Hey everyone, and welcome. Today, we're diving into something we've all been mesmerized by at some point: fire. It's this force of nature that has literally shaped human history. But what is it, really? What's the actual science burning away behind that flame?
So let's start with a little question for you. Think about petrol in a car, a log on a campfire, and the natural gas that fires up your stove. They seem totally different, right? One's a liquid, one's a solid, one's a gas. But on a chemical level, they all share one absolutely critical property. And the answer, well, is actually pretty simple. That one crucial thing they all have in common, they're all fuels. But what does that word fuel really mean? Well, a fuel is just any substance that we can burn to release energy in a useful way. Like the heat that cooks our dinner or the power that gets a car moving. And this powerful chemical reaction, it has a name. And as we're about to find out, it requires a very specific recipe. And that recipe brings us to our first big idea, the fire triangle. This is such a great, simple model that explains the three ingredients that are absolutely necessary for any fire to even exist. And here's the really cool part. This rule is totally universal. It does not matter if you're looking at a tiny little matchstick or a huge raging forest fire. The fundamental science behind them is exactly the same. They all need the same three-part recipe. So what are these three magic ingredients? Let's break them down. First up, you need fuel. That's the thing that's actually burning. Second, you need oxygen, which, luckily for fire, is usually just pulled right out of the air all around us. And third, you need heat, that initial spark, that little bit of energy to get the whole party started. And this is the most important part to remember. The triangle has to be complete. If you take away the fuel, the fire starves. If you take away the heat, it cools down and stops. And if you take away the oxygen, it suffocates. You remove just one of those sides and poof, the fire is gone. This is the single most important principle behind all firefighting. Okay, so the triangle gives us the what. Now let's get into the how. We're going to zoom way in and see what's actually going on at a molecular level when something is burning. So the official scientific word for what we all call burning is combustion. It's simply a chemical reaction where a fuel combines really, really fast with an oxidizer, usually oxygen, to release all that useful energy we talked about, which we see and feel as heat and light. So yeah, to be super clear, burning and combustion are basically the same thing. Burning is just the everyday name for what we see, while combustion is the proper scientific term. But we can actually zoom out even further and see that combustion is just one member of a much bigger family of chemical reactions. And that's because combustion is a really fast, high-energy example of a process called oxidation. This is any reaction where something combines with oxygen. Rust on a car? That's oxidation too. It's just happening incredibly slowly. Fire, on the other hand, is just oxidation happening in fast forward with a whole lot more energy. Okay, so now that we have the right words for everything, how in the world do scientists take this chaotic, energetic, wild process and describe it so neatly on a piece of paper? Well, they use something called chemical equations. And to make this feel real, let's just think about a super common activity. I love this quote from the source material because it's so relatable. It's about lighting a gas barbecue. The fuel inside that gas barbecue is a gas called butane. It's made of carbon and hydrogen atoms, and it's just a perfect example to show us how a combustion reaction gets written down. All right, the simplest way to write it is with what's called a word equation. This basically tells the story of the reaction in plain English. You start with butane and oxygen, they react, that's what the arrow means, and they end up producing carbon dioxide and water. And this shows us the basic structure of pretty much all chemical equations. The ingredients you start with, on the left side of the arrow, are called the reactants, and the all-new stuff you end up with, on the right side, those are called the products. Simple as that. Now, chemists like to use a much more precise way of writing this. It's like their own special shorthand, the symbol equation. I know, it might look a little intimidating, but it tells a much more detailed story. See those big numbers out front? They're not just random. They're there to balance the whole thing. It's a fundamental rule of chemistry. You can't create or destroy atoms in a reaction. You can only rearrange them. So this equation tells us that for every 2 molecules of butane you burn, you're going to need 13 molecules of oxygen. And what you'll get is exactly 8 molecules of carbon dioxide and 10 molecules of water. See, everything is perfectly accounted for. So we've covered the triangle, we've gotten into the nitty-gritty chemistry. Now let's zoom all the way back out to the big picture. Why does this one single reaction matter so much in our world?
Well, the reality is, this single chemical reaction is pretty much the engine of our modern society. It heats our homes, it powers most of our cars, it generates a ton of our electricity, and it cooks our food. Fundamentally, you could say we are a combustion-driven civilization. But look, understanding the science isn't just about big ideas like power plants. That fire triangle we started with? Knowing how that works isn't just theory. It's a vital, practical safety tool that, honestly, everyone should understand. And here is a piece of safety advice that could literally save a life, taken right from our source material. If you ever have an oil fire in a pan in your kitchen, you should never, ever throw water on it. Instead, you cover the pan with a damp cloth. Why? Because you are breaking the fire triangle. You're cutting off its air supply, removing the oxygen. And without oxygen, the fire has no choice but to go out. But for all its amazing uses, there is a massive catch. Remember the products in our little equation? When we burn carbon-based fuels, like petrol, gas, and wood, one of the main byproducts is carbon dioxide, CO2. And as we know, that is a powerful greenhouse gas. And this leaves us with the huge defining question of our time, doesn't it? We have this incredible, powerful reaction that literally built the modern world and gives us energy we rely on every single day. But that exact same reaction is also producing the gases that are warming our planet. So the question is, how do we balance the incredible power of combustion with the urgent needs of our future? That right there is the challenge that lies ahead for all of us.